Hi, this is Ms. Delosier, and these are your notes on impulse. So what is impulse? Well, this will give you a little bit of an idea what impulse is. Impulse is a change in momentum. So hopefully you've already read the notes on momentum. So we're looking at a change in the momentum of an object, and we call that our impulse. So let's look at this car. Let's say that I have this car and it is falling at a speed of 25 meters per second. Let's say it's not changing its speed, it's just 25 meters per second. That's the speed that it's falling. We'll say that that's the terminal velocity of that car. And let's say that the car has a mass of 1,815 kilograms. So I need to go ahead and find the momentum of the car. And so I want to go ahead and do that using the equation P equals m times v. So P is 1815 times 25. That's going to give me a momentum of 45,375 kilogram meters per second towards the ground. So that's my momentum of the car. Now, that's not really the impulse of the car. That's just my momentum of the car. And I told you I was talking about impulse on this. So let's go ahead and let's ask another question. So if the car strikes the ground, what is the impulse? So in this situation, I have the car actually hitting the ground, and I want to know what's the impulse. Now when the car is hitting the ground, the velocity is going to equal 0. So that means that my new momentum is going to be the mass of the car, 1815, times my new velocity, 0, which means the momentum of the car on the ground is 0, right? So if the momentum of the car on the ground is 0, my change in momentum is going to be the difference between the momentum of the car falling, 45,375, minus 0. So that means my change in momentum is actually the full momentum of the falling car, 45,375 kilogram meters per second. Basically, it has that much momentum and then it has none. So what's the difference between them? It's the 45,375, the full thing. That's kind of complicated. So we're going to look at a couple more examples. So let's look at calculating impulse with an actual formula. Let me give you a formula. To find the impulse of an object, we are going to look at the change in momentum. Impulse is represented by the letter J, capital J, and we say that impulse, J, is equal to mass times the change in velocity. So that's the change in an object's speed. It could also be the change in an object's mass, but objects don't normally change masses. So in most of the examples we're going to look at in regular physics, we're going to be looking at a change in velocity, delta V, because that's what that triangle means, right? So let's look at an example. Let's say I have Spider-Man, and he is swinging through the air, and if Spider-Man has a mass of 75 kilograms and is swinging at 10 meters per second, and he sees Juggernaut falling and speeds up to 15 meters per second, what is his impulse? So we're assuming that Spider-Man is going to attempt to save Juggernaut, and he has to speed up to get there. So if his mass is 75 and he's initially going 10 meters per second and he speeds up to 15 meters per second, and that gives us a change in velocity of 5, what is his impulse? What is the change in his momentum? So we're going to look at that, and it's J equals m times delta V, that's 75 times 5, and that means that his impulse is 375 kilogram meters per second in the direction of Juggernaut. I didn't give you an actual direction of that, but presumably he's speeding up in that direction. So that would be his impulse. All right, so let's look at the effect of force on impulse. So when I talk about the effect of force on impulse, I probably need to give you an example. So let's talk about it this way. The greater the force on an object, the greater the change in its momentum. So a large force is going to produce a large change in the momentum. So like if I shove an object really hard, it's going to speed up more. Or if I apply a force for a very long time, that's also going to produce a greater change in the momentum. So let's say I don't shove an object really, really hard, but I'm going to push it for a really long time. That's going to speed it up eventually, right? So we need to go ahead and look at impulse and how it depends on force and time also. So we already know that J equals m times delta v, that the impulse of an object is equal to the change in momentum, mass times the change in velocity. But I'm also going to tell you that impulse can also be written using this equation. And the equation is the impulse is equal to the force times the time. So I can write impulse as force times time, which means I can just write that the force times the time is equal to the mass times the change in velocity. And I know that that's really complicated, but basically I'm finding impulse two different ways and I'm just setting them equal to each other. It's actually not that difficult of a calculation. It's just it's a different looking equation than we're used to seeing. So let's look at an example. Let's say I have a bridge and I have Spider-Man and he's swinging from the bridge and he got to the bridge and he sees Juggernaut falling, right? And he's decided to save Juggernaut even though Spider-Man's a hero and Juggernaut's a villain. And so Juggernaut is falling at a speed of 56 meters per second. And remember, he has a mass of 225 kilograms. And Spider-Man sees Juggernaut falling and he decides to go out and catch him. So if it takes Spider-Man 1 second to stop the Juggernaut's fall, how much force is he exerting on the Juggernaut? So we're going to go ahead and we're going to write down what we know. I know, I got to catch the Juggernaut. I know that the mass is 225. I know that my initial velocity is 56. My final velocity, if I have to stop the Juggernaut, is going to be 0. And my time is equal to 1 second. So I'm going to use this equation. Oh, delta V is going to be negative 56 because my change in velocity is 0 minus 56, V2 minus V1. So I'm going to use this equation. The force times the time is equal to mass times change in velocity. So what do I know? I know everything except force. So I'm going to plug that all in. 225 for my mass, negative 56 for my change in velocity, and then I'm just going to solve for force. And that's going to give me force equals a negative 12,600 newtons. So that's 12,600 newtons up. That means Spider-Man is applying a force of 12,600 newtons up on the Juggernaut immediately. In 1 second, all that force. So basically what that's going to do is that's going to actually kill the Juggernaut because he's not going to be able to survive that much force. Well, I don't know. Juggernaut might be able to. A normal person couldn't survive that much force. What would happen, though, if Spider-Man actually caught the Juggernaut a little slower and somehow cushioned the blow by not doing it quite so fast and drastically? So let's look at that. So let's look at the same problem. So we're going to do the same problem, except now instead of 1 second to stop the Juggernaut, I'm going to say it takes Spidey 10 seconds to stop the Juggernaut. So we're going to do the exact same calculation, but I'm going to replace the time with the number 10. So mass is 225, V1 is 56, V2 is 0, delta V is negative 56, and T equals 10. So if I plug all that in, I'm going to get a force of 1,260 newtons up, right? Which is a significantly smaller force. Is it a small enough force that it doesn't kill the Juggernaut? Well, in this case, it probably doesn't kill the Juggernaut. Would it kill a normal human? Probably would kill a normal human. The other problem is we're talking about 10 seconds. It would have to be a really high bridge in order for Spider-Man to actually catch the Juggernaut over a 10-second fall. Because in most cases, Juggernaut's going to have already fallen into the water and drowned by the time the webbing actually gets to him and cushions his blow, because 10 seconds would be a really long distance fall. You could actually calculate that using the formula D equals 1/2 AT squared, and if any of you feel like doing that and submitting me the answer, maybe I'll give you some extra credit for that.